at how we estimate the parameters alpha and beta in our regression model that was linking, in this case, weight, our dependent variable, with height, our independent variable. And we had assumed that the true model was linear. So that's why you have alpha plus beta times height plus this error term. But now, how do we find which is the best fitted line for the data? And the first thing we need to figure out is how do we express this fitted line? So the fitted line can be written as follows. So we have weight hat, so that's our predicted value for weight for observation I is equal to A plus B times height with I as a subscript. So why do we change the alpha and beta to A and B? Because now we are thinking about estimates. So A is an estimate for the true population alpha, and B is an estimate for the true population beta. Remember that we never observe the true parameters alpha and beta, but we are trying to find a good estimate for what they are. And those estimates are going to be A and B. So weight hat is called the predicted value of weight for observation I. Right? So if we put any given height, we can calculate the predicted height with the estimates that we found in our given sample. Now notice that there's no error term in the fitted line equation. And that makes sense because the equation for a line is just y is equal to a plus bx, and there's nothing else. Now, how do I find the a and b in my model? So I have my x, I have my y, and let's say we have data like this. So intuitively, it makes sense that my line of best fit would be something like this and not something like this, for instance. Okay, we want to have our line go in the middle of our data, but how do we determine what is that middle in a mathematical way? Well, one thing that you may think of is looking at the distance between the actual point and the line and minimizing the sum of the distances. So that would be one of the most logical ways of trying to find the estimates A and B. And that's exactly what we use when we use the method of least absolute deviation. We minimize the sum from I is equal to 1 to n of the absolute value of the difference between weight and weight hat. So weight and weight hat is going to be the difference between the true value of y, of weight in this case, and the predicted value. So my predicted value is going to be the line, okay, that I draw through the data. And here I could draw many, many lines, and we're going to find the one that minimizes the sum of basically distances between the actual value and our prediction. And it makes sense that if we do that, we should get a relatively good estimates for A and B. So historically, one of the reasons why this technique hasn't been used that much, actually, is that if you look at the absolute value function, you will see that it's not differentiable in for all values of x. Okay, especially here at 0, we see that it cannot be differentiated. And so whenever you're trying to minimize a function, normally what you would do is you would differentiate and set to 0. In this particular case, that is not something we could do. So before the use of computers, this would actually be quite a difficult objective function to minimize. So instead, one thing that is much easier to differentiate and a much more popular strategy is just to minimize the sum of the squared differences between the observations and their predicted value. Okay, so instead what we minimize is something that is similar, but the distances have now been squared. So it's the sum between I is equal to 1 and n of weight minus weight hat, so the true weight minus the predicted value of weight, but the whole thing squared, okay? So in other words, we minimize the sum of yi minus yi hat squared, okay? And remember that yi hat can be rewritten as a plus b times x. So this is a method that is called ordinary least squares. And what we do when we do ordinary least squares is just minimizing the sum of the squared residuals. So what do I mean by a residual? The residual is just the term yi minus y hat. Okay, so in this particular instance, it would be, for example, this would be the residual. Okay, so in this case, we do the difference between this point and my predicted value, and that's my residual. So one very important thing to remember is that the residual is very different from the error term. Okay, the error term is equal to yi minus alpha minus beta xi. That is equal to the error term, and the residual is yi minus a minus bxi. Okay, so in one case, we're using the population parameters, and in another case, we're using the estimates. Okay, it's a very, very common mistake to make, to mistake residual for the error term. When we're doing OLS, ordinary least squares, we minimize the sum of squared residuals. So that's it for today's video, and I'll see you in the next one.